Okay, we're going to have composite functions, and then later on we're going to have inverse functions. But for now, we're going to start out with finding the domain of a composite function. And what we're going to do here is look at each function. We have a function f of x and a function g of x. And looking at this, we have to find out what is going to be the domain of each, or what numbers are going to be a part of the set of answers and which ones are going to be excluded. It's pretty common to do in precalculus pretty often, but in these they're a little trickier. So we're going to start out here. This is a composite function, f composite with g at x. So we just have to combine them normally. We're going to use 2 over x plus 1 as the template, and we're going to put the g function inside of the f function. So we have to bring down first of all the 2 over x plus 1, and then you can see there that the x in the bottom part becomes the g. If you can see it this way, the 2x goes into the x of the f function, 2 over x plus 1. Now that we have this bottom part of this function, this composite function, we can find out what the domain is. Now, first of all, as always, you can't have division by 0. This is just a basic golden rule of mathematics. So that 2x part, the function g of x, can't have a 0 in the denominator. So automatically we know in our domain x cannot equal 0. Now we have to find out for this composite, in the denominator we have 2 over x plus 1. In this part we have to make sure that also, again, for a second time, we don't get 0 in the denominator. To do this, we set the denominator 2x plus 1 equals 0, and then just simply solve for x. And doing just normal algebra here, we're going to have first of all the negative 1 on the right side, and then 2 over x equals negative 1. That x is going to come over so that it'll be negative x equals 2. But that negative sign goes to the other side so that we get x equals negative 2. Now this means, if you look back at the denominator, if you look at it, if you put a negative 2 in there with the x's, that's going to cause a negative 1. And then a negative 1 plus 1 is going to result in 0. And that means you're going to have division by 0, again, which is not allowed. So our answer for this part is that x cannot equal 0 for the g function, because the x is below the 2. But also then, when you combine the two functions, when you create the composite, the denominator cannot equal 0 once again, so you cannot have a negative 2 in that denominator, because it'll also result in 0. So our domain is all real numbers of x except 0 and negative 2. We're going to move on to something a little different here. Not that different, but this is inverse functions. And an inverse function, we want to show that when you combine them, when you combine the f composite with g at x, if you do all the operations, the algebra and the arithmetic, it should result ultimately in x. And that's how you know that they are actually the inverse of each other. You have to check it both ways, but this one's pretty apparent. Once we work through it, you'll be able to see it. But in the next step here, I'm going to show you how to see that this is going to result in x. Again, we would just want to see if f composite with g at x result in just x. And this is the steps it's going to go. You're going to bring down the 2x minus 6. The big brackets there is emphasized there to show you that that x, the 2x, which is the big box there, minus 6 is where the g is going to go into, where the composite happens. As we can see, the function g goes into that space right there, so that all of the x of the 2x minus 6 is now 1/2 times x plus 6. Now again, I was saying how these are pretty easy to see. Sometimes, not always. This one in particular is actually pretty easy to see, because you can see the 2 and the 1/2 are going to cancel each other out. 2 times 1/2 is immediately 1x, which then just leaves x plus 6, and then the 6 and the minus 6 immediately cancel each other out, leaving just a 0. So you have, after those two operations, just x left. There's always one last double check of these problems. What we did here is f composite g at x equals x. You also have to check it the other way also. You also have to check it that g composite f at x equals x. This one, it's so apparent that the steps are easy to work out even just by looking at it. But when they work out that way, both ways, both f composite g and g composite f, then you do have an inverse function.